Good morning, everyone. Thank you very much for coming in on time as requested. It's my pleasure and my honor to introduce Professor Simon Moore from the University of Cambridge, who I met probably a decade ago through a New Zealand connection, of course, as you do. Professor Michael Kelly, who at the time was the Prince Philip Professor of Engineering and Technology at the University of Cambridge at Trinity College.
Yeah, Trinity Hall.
Which, of course, is just a guy from New Plymouth. So I went to visit him, and then we had a long chat about this and that and those, and then invite me to meet Professor Moore. And that was probably 2016, 17 or something. And what I want to highlight is not just patience and perseverance, that Multicore world is here and waiting for you. Thank you very much.
Well, thank you for the invitation. Yeah, it's great to be here. I'm actually on sabbatical. I've been on the faculty for 26 years. It's the first time I managed to get sabbatical and get away, which is nice, partly because my kids are now adults. But I'm at the University of Victoria in Wellington for a bit, collaborating with people there. It's been great to come down. I'm a computer architect. I work with lots of other people, as you can see from the list. Sort of lead people. Robert Watson is really a security and operating systems expert. Peter Zuhl is expert in formal verification. Peter Neumann is a bit of an old hand. He's actually in his 90s doing security stuff, and Bookstave is another operating system person. But it means that with this team of people, we can do everything from gates to applications and everything in between. So operating systems, compilers, linkers, we can verify stuff, we can build prototypes. We've had, for this work, quite a lot of sponsors, quite a few of them in the US, which is making me nervous at the moment because we still have US funding. Fortunately, we haven't had a stop notice yet. I was going to just very briefly say another link, a very influential link between New Zealand and Cambridge. So, I mean, Rutherford came to Cambridge and subsequently went to McGill. And by the way, this is a rather poor picture that I took from an exhibit in Christchurch. So you can go and see these papers from his Nobel Prize that he won. He went on to be the director of what's called the Cavendish Laboratory in Cambridge, which is the physics department. And he encouraged people to basically look inside the atom. And so things that were discovered at that time were things like the neutron. And he was hugely influential. He was director for a long time. And I've seen that department benefited enormously. I'm in computer science, which is right across the road from the Cavendish these days. We started off building computers. So Professor Sir Maurice Wilkes, after the Second World War, he'd actually worked on radar, which is one reason why he was allowed to work on computers, because a lot of the people at Bletchley Park who were working on things like Colossus, the UK government wanted to keep it so secret. So people like Tommy Flowers, who led the Colossus work, he was banned from ever working on computers ever again. He instead automated the UK phone exchange and made it digital. But it was quite interesting. Whereas Maurice knew nothing about the code-breaking activity that had gone in the UK. He'd actually worked on radar. And one of the things he'd worked on with the physics department, so there's a link there, are mercury delay lines, which are used for echo cancellation in radar systems. And he realized he could use these as basically bit serial memories. And EDSAC is a bit serial computer, and everything is timed off the mercury delay lines, which is quite amazing. So the entire computer's timed off the memory. Very influential in its time. It was pushed into service. It was a real practical machine. It could do real calculations, and it's credited with doing the calculations for 3 Nobel Prizes. In fact, one of the Nobel Prize acceptance speeches refers to EDSAC like a colleague, which I find quite extraordinary. Moving on, in the 1970s, the department looked at things like capability machines. Apologies for the terrible model. which really didn't work. Well, I mean, it sort of worked. It was very sophisticated protection mechanisms. It ended up being very complicated. And really, the industry went down the route of virtual memory, which has got its own complexities, but is in many ways simpler. I then, in the late 90s, early 2000s, started building up the computer architecture group again, because we had sort of gone off and done other things in the department, a lot on operating systems and networks and all sorts of other stuff. But I'd really moved away from doing computer architecture. So I've been building the computer architecture group back up, really, the last sort of 25 years. Right, today I'm going to tell you about CHERI. So a quick intro to CHERI. What is it? How we've deployed software. What are some of the architecture and microarchitecture challenges, and some conclusions. And this project is very far advanced, and we're trying to really get it deployed in industry. So what is CHERI? Well, it's a modern take on a capability machine. It's actually very different from CAP. It very much learns from sort of RISC type microarchitecture and architecture. And it's there to meet the following challenges. So we observe that memory safety is a major problem. So technical director at NTSU, actually now at AWS, Ian Levy, said, buffer overflows have not objectively gone down in the last 40 years, and the impact of buffer overflows have, if anything, gone up. And that's just one example of a memory safety vulnerability. Matt Miller from the Microsoft Security Response Center, said that year after year, all of the Microsoft vulnerabilities, about 70% of them are memory safety bugs. This is kind of crazy. So what's the industry doing about it? This isn't just a Microsoft problem. Google report. It's funny, this 70% number keeps coming up over and over again. Chromium browser, similarly. You'll see if you use Chrome that you get a security update about every 2 days. And it's another security vulnerability that they've identified. It's a major problem. Economically, I mean, I mentioned on the panel yesterday, cybercrime is, now the economic impact of cybercrime is about twice that of the illegal drugs trade worldwide. So it's a major problem. And at the moment, industry doesn't seem to be tackling the root causes of these problems. And that's one reason why our team and others were initially funded by DARPA starting in 2010 to look at what can you do to fundamentally improve security. Let me just give you an example of a bug, because this one is just particularly easy to explain. So the Heartbleed bug was actually a vulnerability identified in 2012. So this is in the TLS protocol. So this is used to, secure web transactions. And one of the things that's interesting is all the cryptographic protocol stuff, that was really thoroughly analyzed. However, there was also this little heartbeat message used to keep the network connection live. And explaining with XKCD comic, basically, if the client sort of says, right, are you still there, server? Say potato. The server would say potato. And similarly, server, say bird. It's 4 letters. And sure enough, it says bird. Then the client gets a bit clever and it says, say hat. By the way, hat's 500 letters long. And I mean, this is just embarrassing, but you get a buffer overread attack. Not only do you get hat, but it just reads the rest of the buffer out. And you could read all sorts of secret information. And basically this allowed people to impersonate banks. It allowed fraudulent transactions. This is a big deal, right? And it's just crazy. Why should this sort of bug occur? So how can we do better? Well, we could use languages like Rust. And I would argue that Rust actually is a great language. Really encourage people to use it. Great for new code. The real problem is that we've got this vast body of legacy code. The other issue with Rust is there's still quite a lot of unsafe Rust. And so, for instance, the string libraries, when I last looked, were all in unsafe Rust. And that's a bit of a concern because you often get problems around string libraries. Our approach is rather different. So we want to make C, C++, and other languages, so it's language agnostic, and we're going to recompile your code and preserve much more information about objects and structures and so on that you're referencing, because we can actually infer a lot about how you intended to access memory. You know, when in the case of the Heartbleed example, the programmer never intended to, introduce that vulnerability. So that was pretty crazy. It turns out it was actually just a one-line fix. But actually, if you compiled that code with the CHERI system, it mitigates the vulnerability completely without you even knowing what the vulnerability is. So how do we do it? Well, at the lowest level in the hardware, we basically add a new data type. So it's a bit like adding floating point to a system that only does integers. Here we're going to add a new data type that is specifically for addresses. We call it a capability. It's there's a long history of sort of capabilities in security. And the fundamental idea with the capability, because you can have cryptographic capabilities and all sorts of things, is that a capability is a token of authority that has provenance. You know, you can't just magic one out of thin air, and you can use that to do something. Here, we're going to use it to access memory. And the basic idea is actually very simple. So you've got your 64-bit address. We also have a version for 32-bit machines. You've got some compressed bounds information and permissions, and those basically allow you to access that region of memory. And for most code, you just recompile the code, and it just works, okay? So it doesn't really matter. In fact, we realized that an awful lot of code that we've been trying has had to go through the 32-bit to 64-bit transition. And so they had to become pointer length agnostic. And that's actually been really useful, because as soon as you're pointer length agnostic, saying, oh, look, your pointers are twice as big, turns out not to be a problem. One of the key things here is that we have guarded manipulation of these capabilities. So the hardware, the instruction set, the processor architecture, guarantees things like monotonicity. What do I mean by that? Well, you cannot increase your bounds or permissions. Even if you're in kernel code, you can only you could hang on to a very powerful capability that can access a lot of memory. And so, you could ask some authority, for instance, that's got hold of a very powerful capability to allocate you, say, a region of memory, which you need from memory allocation. But once you're given, once you have this set of capabilities, you are constrained by that set. And we've done formal verification work to basically demonstrate that, there can be no sequence of code that allows you to expand your permissions or bounds. And using that, you get things like integrity properties and provenance. Pointers don't come out of thin air. One thing that amazed us, we thought C programmers would do really grimy things with pointers. And having recompiled millions and millions of lines of code and done operating system stuff, turns out they don't really. It was one of those sort of big experiments that was rather welcome to see it wasn't a problem. We have bounds so that you can't mix one object up with another, or something that's on the heap with globals, or something that's on the stack. You've got this monotonicity property and permissions that I've just mentioned. And the net result is we get very strong spatial memory protection. And actually, using some other techniques, we can then get also good temporal memory protection as well. And all by just recompiling your software. The other neat trick is that we can get very strong compartmentalization. So currently, things like the Chromium browser use process-based compartmentalization. So for instance, each tab in your Chromium browser will run in a separate process. So it's in a separate virtual address space. Similarly, Apple do this with things like iPhones. iOS will break lots of things up into separate processors. So for instance, if the little keyboard pops up, that runs in a separate process. If it wants to do key completion based on your address book, it doesn't get access to your address book. It can just query another process that has access, and so on. And so that's one way that Apple have sort of locked things down. The problem with that sort of approach is if you have large numbers of active virtual address spaces, your translation look-aside buffer, your cache of virtual addresses, starts getting thrashed. And in fact, iPhone processors have absolutely enormous TLB structures, multi-level and very large TLB structures to try and cope, but it doesn't scale. CHERI, on the other hand, you can give a piece of code a set of capabilities, and it is constrained within that set of capabilities. And so we can actually have an arbitrary number of compartments with no additional cost. And also communication between compartments is incredibly cheap. You can set up, specific areas where you want to share. So you actually get an enormous performance win here if you want to do compartmentalization. And I would argue you want to do compartmentalization because it reduces the attack surface, which is rather important. At the moment, we build ever bigger systems with more and more code. And from the attacker's point of view, this is an ever larger attack surface. If you do compartmentalization, so you compartmentalize libraries, for instance, you reduce the attack surface and fundamentally improve security. We've got a lot in open source, so all of this technology is available open source. We've done a lot with ARM, also in the open, which is interesting given they're an IP company. But we've been doing a lot recently around RISC-V. Our original prototypes were on MIPS, because at that point RISC-V didn't exist. ARM didn't even have a 64-bit processor when we started in 2010. But we now have, open source processors, documentation, formal specification. In fact, we contributed the golden model of RISC-V in a language called Sail to RISC-V International. So we actually did the original formal model for RISC-V for them. We've got simulators, we've got Clang LLVM toolchain, and we've got various operating systems. Let's talk a little bit about software deployment. I'm not going to say too much. There's a lot we could talk about. Obviously, the main architecture provides just these primitives, but software can use it in all sorts of ways. I mean, bounded pointers is just, tip of the iceberg.
Yes.
In the same way that, for instance, a processor will understand that it has to deal with virtual addresses and it knows what page tables are. But in a way, the processor doesn't know what a process is. That's a concept you build on top. If you had ideas of guard pages, for instance, the processor doesn't know what a guard page is. This is all a software abstraction of how you use that mechanism. Similarly, with capabilities, you can build all sorts of mechanisms on top of the system. And some of it we're still exploring. So the low-hanging fruit is you get very efficient fine-grained memory protection for C, C++. There's also a Rust prototype, so we can actually make your unsafe Rust safe, which is pretty neat. But another big win is this scalable compartmentalization, and where you get really enormous performance boosts over current process-based techniques. On the compartmentalization stage, we currently have a sort of early version of library compartmentalization. So any dynamically linked library, we can just say for an application, just wrap that in a compartment. So, that compartment now no longer gets the ambient privileges of the user. It's really constrained by what it can do. And one of the demos I didn't bring an ARM Morello box running all this stuff, but we quite often like to give presentations of it. And we just use the Ocular PDF viewer, and Ocular, from memory, I think calls 163 different libraries. So we can run Ocular and all these other things all in compartments, and we can have the whole system running using library compartmentalization, and the performance is just fine. That's pretty neat. There's also stuff we're doing around sort of co-process stuff. So if you've got something like a Chromium browser, which has a process-based model, how can we transform that process-based model in Chromium into something that's CHERI-like and yet still look somewhat process-like, but more efficient? We've done operating system stuff. So really the sort of highlight numbers are numbers of lines of code change are very small. And particularly when you get things like programs and libraries, the number of lines of code change are very small. So this will include, just standard build stuff you get with a distribution, even fairly large things like Postgres database and so on, and Nginx. There's been a desktop pilot study which took 6 million lines of, this was just a 3-month study with one person. They took 6 million lines of code with various desktop applications, basically recompiled them for CHERI and then found out what bugs materialize. Because one of the things you do find with CHERI is it just identifies bugs in your code. And but very low numbers of lines of code changed to basically fix the bugs, and occasionally get rid of some memory allocators that don't understand about CHERI. Those are the main areas where we get very good mitigation rates against past vulnerabilities in this code. Done lots of work about temporal memory safety. That gets quite involved, and I don't really have time. I'm a microarchitect, so forgive me, I'll tell you a little bit about microarchitecture. One of the things we add, excuse me, I've got a bit of a scratchy throat, so Englishman with his tea, sorry. One of the things we add is a validity tag for every capability. And from a security point of view, this is absolutely critical. It's a hidden tag. So we don't need any crypto at all. We do need this hidden validity tag. So for every 128 bits of memory, we have a hidden validity tag. And that's just one of those things where I talk to people in industry and hardware designers go, this sounds horrible. So we've worked through this. We worked through it with ARM as well. It's very easy for registers. It's very easy in the caches. It's very easy to just add that extra bit. In registers, actually, we make the integer registers twice as wide, which turns out to be a good compromise between complexity of things like register coloring and all that sort of stuff, trying to avoid needing to do more of it. We add tag bits in the caches, so that all just goes along with the cache lines. That's very straightforward. The real problem is when we get to DRAM, because, well, DRAM comes in power of 2 sizes, and we're basically saying that all of our memory is units of 129 bits. So there are a couple of approaches, and in fact, ARM's implemented both. One is to use basically additional DRAM, so things like ECC bits. It turns out there are some tricks you can play, still get a certain amount of ECC and still get the tags in. The one that we actually prefer in many ways is to add a little tag cache. And so we store the tag bits in the upper 1% of DRAM. And we did some initial work on this, and a very simple cache worked well enough. We published this along with some other work at one of the top conferences, and we were sort of seeing 3% DRAM overhead. When we showed the overheads to ARM, they said, that's not acceptable, because all the DRAM overheads, that's quite a lot of extra power. So we went away and looked at ways of compressing this tagging scheme. I go to the next one. One of the basic ideas is if you imagine just having a 2-level table. So the lowest level, the leaf table, basically has 1 bit for every 128 bits of memory. And a 1 says there's a tag there, and a 0 says there isn't. And then you can have another table that's slightly further up that says, for example, does this page have any tags in it or not? Because you end up with lots of pages with no tags at all. Moreover, before you actually even allocate memory, of course, typically the OS zeros memory for you. And one of the things we discovered is we can sort of get the hardware to work quite nicely. So when you do memory allocation, you're allocated zeroed regions of memory, and we can deduce in this root table that there are no tags there. So in fact, when you start to write your first capability to this newly allocated memory, we can already know, there are no tags. We don't need to look this up in DRAM. There are no tags. So you can just fabricate the leaf level table. So there's all sorts of tricks we can do, lots of optimizations. And basically, it gets the overheads for most applications down to 0. And if you've got something that's incredibly pointer heavy, we see a few minor overheads. Yeah, we have a level of a job then publishing this next paper. It ended up going to ICCD. And just for junior members who get frustrated about reviewers, so, we did an anonymous submission, so we critiqued our own prior work. And one of the reviewers said, why are you criticizing those nice people from Cambridge? They even used the words, those nice people from Cambridge, in the review. Their previous work showed only 3% overhead. It's like, guys, we are those nice people from Cambridge. We needed to do better. And this was one of the problems, I think, you work with industry. We were working with Richard Grissonthwaite, the chief architect at ARM, and he said, well, we have to do better. We did do better, and then we had a devil of a job publishing it, which is really frustrating. We also did a load of work on compressing capabilities, but that's a whole subject in itself, and lots of other microarchitectural techniques. Let's talk about bringing CHERI to the market. So how do you actually take this technology? So if you think about sort of technology readiness levels, in the first sort of 4 years of this work, we did the initial research. It all looked quite plausible. And I think often in academia, you sort of stop at that point. You've got all your simulation results. You've got, some initial benchmarks, and it all looks good. And in fact, that's by and large all you need for a lot of the top conferences. We do like to build things. So we tend anyway, and we had quite a bit of DARPA funding where they wanted us to build prototypes. So we did get as far as, starting to build FPGA prototypes, actually do the full OS, really bring it up on a, fairly realistic processor. So yeah, we got that far. And then we started collaborating with ARM and others. We had an initiative in the UK, which is just finishing, called the Digital Security by Design Initiative, which is quite a big chunk of money. And that allowed us to do a prototype with ARM. So we actually did a 7-nanometer prototype using Neoverse N1 processor. And that's the sort of thing you just can't do in academia. ARM took an existing system on chip that they had. They took their team that had done the Neoverse N1. They gave them 15 months. So they threw 100 engineers at it for 15 months to get the chip out of the door. Yeah, we've got 1,000 of these desktop systems, and those have been going to lots of industry and academic players. A lot in the UK. It was a UK-funded initiative, but also a lot in the US. So that was a pretty big deal. And just very expensive. Just the mass cost for that chip were $10 million. We've been able to then throw the technology over the wall to various people. Microsoft did an interesting report back in 2020. So they looked at all their 2019 vulnerabilities, and in this 42-page report, they conclude that CHERI would have deterministically mitigated 2/3 of all the vulnerabilities they'd seen. So these are all the things they'd had to patch, to the point where they wouldn't have even needed to have issued a patch, which is a very high bar. So that's great. So we're getting to the point where the security people really like it. In fact, Microsoft Research set up this little project to do something in the embedded system. So the CHERI for IoT, which is a 32-bit RISC-V system, that code's open sourced. That's being picked up by Low Risk in Cambridge, who've been working on things like OpenTitan with Google. And you can now buy that from suppliers like Mouser. So you can actually go and buy one of these, although it is just an FPGA board. We've got companies like Codasip, who announced that they're going to ship product. We've been doing a lot I've been doing a lot actually leading the sort of standardization effort with RISC-V International. So we now have a complete spec that's going through a ratification process as an official extension. And then we've been also talking to various agencies. We've been seeing reports around memory safety coming out. So this is, November 22. There's a Five Eyes report came out. So this includes New Zealand, of course, and Australia, US, Canada, UK. And in that, they recommend us the Secure Hardware Foundation CHERI, which is rather nice. And we also appeared in a White House report that came under the previous administration back in February. There's been lots of industrial evaluation. So all of these companies have had Morello boxes. They've all ported code. They've all seen the benefits. And this is all going really great. I mean, people say, yeah, we want it. In fact, all of these companies, a lot of UK companies, and they say, well, we want to buy them. And at the moment, ARM is saying, yeah, but to do the full version, it's quite a lot of engineering work. And we need somebody who's going to issue an order for 100 million units. And none of those people are going to buy 100 million units. I haven't talked to my friend Eben at Raspberry Pi. The Raspberry Pi Foundation initiative came out of my department. And he said, well, they're shipping about 10 million units a year. So they're getting close to the sort of volumes needed, but not there yet. So that's a bit of a problem. So we've been focusing a lot on RISC-V because I think there's a lot, it's easier to get into the embedded space. And with CODASIP and others, we now have a CHERI Alliance, so an industrial club. There's quite a lot of commercial activity. So we've got this ARM Morello prototype, and there's a hot chips paper from 22 about that. CODASIP have announced that they've got both little embedded cores and application class cores ready to go. Microsoft, I said, released CHERIoT, and there's now a little startup company, SCI Semi, who are on track to produce a chip. Google are doing various things. There's a limit to how much I'm allowed to say there. And there's another company, Sequoia, who are also looking at a sort of memory-safe AI chip. So if you'd like further reading, we actually have an ACM article that I think was released about 1 or 2 weeks ago. It's a thought piece with various academics and industrial players. So then we move to conclusions. So what does CHERI provide? Well, it gives us completely deterministic mitigation of memory safety vulnerabilities. And deterministic is really important. There's an awful lot of statistical techniques that are currently being used. And we've learned over the years that by and large, statistical techniques can be broken. This is completely deterministic, completely non-bypassable. So that's good. We get efficient pointer integrity and bounds checking, including for legacy languages. So it eliminates buffer overflow, buffer overread attacks, and so on. And we get proven, highly scalable, efficient compartmentalization. And this is really important for security. There's an old idea called the principle of least privilege. And security people have been talking about it for a long time, but there hasn't really been a good way of exploiting the idea, because the architecture doesn't really support things like compartmentalization, but CHERI does. And I think that's really important, because if you can, for instance, there have been execute vulnerabilities in libraries like libpng. So you download an image off the web into some application browser, whatever, you run it through libpng and you get an execute vulnerability. I mean, this is just nuts. It's quite difficult to do a security audit on all these different libraries, but with CHERI, it's very easy to compartmentalize it. And you could say to something like libpng, well, it's in a compartment, doesn't get OS access. It's only going to transform things from one buffer to another buffer. That's all it can do. And by the time you've done that, it can't really do anything naughty, basically. And we get an enormous performance improvement over process-based compartmentalization. And finally, we're working with industry and the open source community to deploy the technology. I think the challenge we're having now is any sort of security comes with a cost. And CHERI, actually, the overheads are incredibly low. In fact, the main cost is that your memory footprint grows because your pointers get bigger. Through the ARM work, they've applied CHERI to the Neoverse N1. We know now it doesn't hurt clock frequency, doesn't change the pipeline structure. If you're running legacy code, it'll still run non-CHERI code. You get no overheads at all. And if you want to use CHERI, you get a very small overhead just to do with the extra memory footprint. So we think this is great. However, when I talk to people in industry, they see it as, well, we don't think we want to go first. And there's a little bit of cost because it's a little bit of extra area, and so on and so forth. But also, I think fundamentally, they have no idea. And if I talk, I've done a lot of work with ARM over the years. They know how to sell performance. They know how to market performance, and they know how to market energy efficiency. They have no idea how to market security. We also realize that there are really no standards for security. There's for things like cryptography, but if you want to sort of mitigate vulnerabilities, there are no sort of standards out there. So we've been talking to US government people in particular, and NIST and others. What can we do about this? Because they were also frustrated, because there's basically, when they do government procurement, there's no check boxes around security, which seems nuts. So we're trying to do that, but if you've got any ideas, I'm all ears. Excuse me, and with that, I'll finish.
Wonderful. Thank you very much.